This right here is what we're going to build to this video, a certain animated approach to thinking about a super important idea from math, the Fourier transform. For anyone unfamiliar with what that is, my number one goal here is just for the video to be an introduction to that topic. But even for those of you who are already familiar with it, I still think that there's something fun and enriching about seeing what all of its components actually look like. The central example to start is going to be the classic one, decomposing frequencies from sound. But after that, I also really want to show a glimpse of how this idea extends well beyond sound and frequency into many seemingly disparate areas of math and even physics. Really, it is crazy just how ubiquitous this idea is. Let's dive in. This sound right here is a pure A, 440 beats per second, meaning if you were to measure the air pressure right next to your headphones or your speaker as a function of time, it would oscillate up and down around its usual equilibrium in this wave, making 440 oscillations each second. A lower pitch note, like a D, has the same structure, just fewer beats per second. And when both of them are played at once, what do you think the resulting pressure versus time graph looks like? Well, at any point in time, this pressure difference is going to be the sum of what it would be for each of those notes individually. Which, let's face it, is kind of a complicated thing to think about. At some points, the peaks match up with each other, resulting in a really high pressure. At other points, they tend to cancel out. And all in all, what you get is a wave-ish pressure versus time graph that is not a pure sine wave. It's something more complicated. And as you add in other notes, the wave gets more and more complicated. But right now, all it is a combination of 4 pure frequencies. So it seems needlessly complicated given the low amount of information put into it. A microphone recording any sound just picks up on the air pressure at many different points in time. It only sees the final sum. So our central question is going to be how you can take a signal like this and decompose it into the pure frequencies that make it up. Pretty interesting, right? Adding up those signals really mixes them all together. So pulling them back apart feels akin to unmixing multiple paint colors that have all been stirred up together. The general strategy is going to be to build for ourselves a mathematical machine that treats signals with a given frequency differently from how it treats other signals. To start, consider simply taking a pure signal, say with a lowly 3 beats per second, so that we can plot it easily. And let's limit ourselves to looking at a finite portion of this graph. In this case, the portion between 0 seconds and 4.5 seconds. The key idea is going to be to take this graph and sort of wrap it up around a circle. Concretely, here's what I mean by that. Imagine a little rotating vector where at each point in time, its length is equal to the height of our graph for that time. So high points of the graph correspond to a greater distance from the origin, and low points end up closer to the origin. And right now, I'm drawing it in such a way that moving forward 2 seconds in time corresponds to a single rotation around the circle. Our little vector drawing this wound up graph is rotating at half a cycle per second. So this is important. There are 2 different frequencies at play here. There's the frequency of our signal, which goes up and down 3 times per second. And then, separately, there's the frequency with which we're wrapping the graph around the circle, which at the moment is half of a rotation per second. But we can adjust that second frequency however we want. Maybe we want to wrap it around faster. Or maybe we go and wrap it around slower. And that choice of winding frequency determines what the wound-up graph looks like. Some of the diagrams that come out of this can be pretty complicated, although they are very pretty. But it's important to keep in mind that all that's happening here is that we're wrapping the signal around a circle. The vertical lines that I'm drawing up top, by the way, are just a way to keep track of the distance on the original graph that corresponds to a full rotation around the circle. So lines spaced out by 1.5 seconds would mean it takes 1.5 seconds to make one full revolution. And at this point, we might have some sort of vague sense that something special will happen when the winding frequency matches the frequency of our signal, 3 beats per second. All of the high points on the graph happen on the right side of the circle, and all of the low points frequencies happen on the left. But how precisely can we take advantage of that in our attempt to build a frequency unmixing machine? Well, imagine this graph as having some kind of mass to it, like a metal wire. This little dot is going to represent the center of mass of that wire. As we change the frequency and the graph winds up differently, that center of mass kind of wobbles around a bit. And for most of the winding frequencies, the peaks and the valleys are all spaced out around the circle in such a way that the center of mass stays pretty close to the origin. But when the winding frequency is the same as the frequency of our signal, in this case 3 cycles per second, all of the peaks are on the right and all of the valleys are on the left, so the center of mass is unusually far to the right. Here, to capture this, let's draw some kind of plot that keeps track of where that center of mass is for each winding frequency. Of course, the center of mass is a two-dimensional thing. It requires 2 coordinates to fully keep track of, but for the moment, let's only keep track of the x-coordinate. So for a frequency of 0, when everything is bunched up on the right, this x-coordinate is relatively high. And then as you increase that winding frequency, and the graph balances out around the circle, the x-coordinate of that center of mass goes closer to 0, and it just kind of wobbles around a bit. But then, at 3 beats per second, there's a spike, as everything lines up to the right. This right here is the central construct, so let's sum up what we have so far. We have that original intensity versus time graph, and then we have the wound up version of that in some two-dimensional plane. And then, as a third thing, we have a plot for how the winding frequency influences the center of mass of that graph. And by the way, let's look back at those really low frequencies near 0. This big spike around 0 in our new frequency plot just corresponds to the fact that the whole cosine wave is shifted up. If I had chosen a signal that oscillates around 0, dipping into negative values, then, as we play around with various winding frequencies, this plot of the winding frequency versus center of mass would only have a spike at the value of 3. But negative values are a little bit weird and messy to think about, especially for a first example, so let's just continue thinking in terms of the shifted up graph. I just want you to understand that that spike around 0 only corresponds to the shift. Our main focus, as far as frequency decomposition is concerned, is that bump at 3. This whole plot is what I'll call the almost Fourier transform of the original signal. There's a couple small distinctions between this and the actual Fourier transform, which I'll get to in a couple minutes, but already you might be able to see how this machine lets us pick out the frequency of a signal. Just to play around with it a little bit more, take a different pure signal, let's say with a lower frequency of 2 beats per second, and do the same thing. Wind it around a circle. Imagine different potential winding frequencies, and as you do that, keep track of where the center of mass of that graph is, and then plot the x-coordinate of that center of mass as you adjust the winding frequency. Just like before, we get a spike when the winding frequency is the same as the signal frequency, which in this case is when it equals 2 cycles per second. But the real key point, the thing that makes this machine so delightful, is how it enables us to take a signal consisting of multiple frequencies and pick out what they are. Imagine taking the 2 signals we just looked at, the wave with 3 beats per second and the wave with 2 beats per second, and add them. them up. Like I said earlier, what you get is no longer a nice pure cosine wave, it's something a little more complicated. But imagine throwing this into our winding frequency machine. It is certainly the case that as you wrap this thing around, it looks a lot more complicated. You have this chaos and chaos and chaos and chaos, and then whoop, things seem to line up really nicely at 2 cycles per second. Then as you continue on, it's more chaos and more chaos, more chaos, 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 whoop, things nicely align again at 3 cycles per second. And like I said before, the wound up graph can look kind of busy and complicated, but all it is the relatively simple idea of wrapping the graph around a circle. It's just a more complicated graph and a pretty quick winding frequency. Now what's going on here with the 2 different spikes is that if you were to take 2 signals and then apply this almost Fourier transform to each of them individually, and then add up the results, what you get is the same as if you first added up the signals and then applied this almost Fourier transform. And the attentive viewers among you might want to pause and ponder and convince yourself that what I just said is actually true. It's a pretty good test to verify for yourself that it's clear what exactly is being measured inside this winding machine. Now this property makes things really useful to us because the transform of a pure frequency is close to 0 everywhere except for a spike around that frequency. So when you add together 2 pure frequencies, the transform graph just has these little peaks above the frequencies that went into it. So this little mathematical machine does exactly what we wanted. It pulls out the original frequencies from their jumbled up sums, unmixing the mixed bucket of paint. And before continuing into the full math that describes this operation, let's just get a quick glimpse of one context where this thing is useful: sound editing. Let's say that you have some recording and it's got an annoying high pitch that you would like to filter out. Well, at first, your signal is coming in as a function of various intensities over time, different voltages given to your speaker from 1 millisecond to the next. But we want to think of this in terms of frequencies. So, when you take the Fourier transform of that signal, the annoying high-pitched is going to show up just as a spike at some high frequency. Filtering that out by just smushing the spike down, what you'd be looking at is the Fourier transform of a sound that's just like your recording, only without that high frequency. Luckily, there's a notion of an inverse Fourier transform that tells you which signal would have produced this as its Fourier transform. I'll be talking about that inverse much more fully in the next video, but long story short, applying the Fourier transform to the Fourier transform gives you back something close to the original function. Kind of. This is a little bit of a lie, but it's in the direction of truth. And most of the reason that it's a lie is that I still have yet to tell you what the actual Fourier transform is, since it's a little more complex than this x-coordinate of the center of mass idea. First off, bringing back this wound up graph and looking at its center of mass, the x-coordinate is really only half the story, right? I mean, this thing is in 2 dimensions. It's got a y-coordinate as well. And as is typical in math, whenever you're dealing with something 2-dimensional, it's elegant to think of it as the complex plane, where this center of mass is going to be a complex number that has both a real and an imaginary part. And the reason for talking in terms of complex numbers, rather than just saying it has 2 coordinates, is that complex numbers lend themselves to really nice descriptions of things that have to do with winding and rotation. For example, Euler's formula famously tells us that if you take e to some number times I, you're going to land on the point that you get if you were to walk that number of units around a circle with radius 1, counterclockwise, starting on the right. So, imagine you wanted to describe rotating at a rate of 1 cycle per second. One thing that you could do is take the expression e to the 2 pi times I times t, where t is the amount of time that has passed. Since for a circle with radius 1, 2 pi describes the full length of its circumference. And this is a little bit dizzying to look at, so maybe you want to describe a different frequency, something lower and more reasonable. And for that, you would just multiply that time t in the exponent by the frequency, f. For example, if f was 1/10, then this vector makes 1 full turn every 10 seconds, since the time t has to increase all the way to 10 before the full exponent looks like 2 pi I. I have another video giving some intuition on why this is the behavior of e to the x for imaginary inputs, but for right now, we're just going to take it as a given. Now, why am I telling you this, you might ask? Well, it gives us a really nice way to write down the idea of winding up the graph into a single tight little formula. First off, the convention in the context of Fourier transforms is to think about rotating in the clockwise direction. So let's go ahead and throw a negative sign up into that exponent. Now, take some function describing a signal intensity versus time, like this pure cosine wave we had before, and call it g of t. If you multiply this exponential expression times g of t, it means that the rotating complex number is getting scaled up and down according to the value of this function. So you can think of this little rotating vector with its changing length as drawing the wound up graph. So think about it, this is awesome. This really small expression is a super elegant way to encapsulate the whole idea of winding a graph around a circle with a variable frequency, f. And remember, the thing we want to do with this wound up graph is to track its center of mass. So think about what formula is going to capture that. Well, to approximate it at least, you might sample a whole bunch of times from the original signal, see where those points end up on the wound up graph, and then just take an average. That is, add them all together as complex numbers, and then divide by the number of points that you've sampled. This will become more accurate if you sample more points which are closer together. And in the limit, rather than looking at the sum of a whole bunch of points divided by the number of points, you take an integral of this function divided by the size of the time interval that we're looking at. Now, the idea of integrating a complex valued function might seem weird, and to anyone who's shaky with calculus, maybe even intimidating, but the underlying meaning here really doesn't require any calculus knowledge. The whole expression is just the center of mass of the wound up graph. So great! Step by step, we have built up this kind of complicated, but let's face it, surprisingly small expression for the whole winding machine idea that I talked about. And now there is only one final distinction to point out between this and the actual honest-to-goodness Fourier transform. Namely, just don't divide out by the time interval. The Fourier transform is just the integral part of this. What that means is that instead of looking at the center of mass, you would scale it up by some amount. If the portion of the original graph you were using spanned 3 seconds, you would multiply the center of mass by 3. If it was spanning 6 seconds, you would multiply the center of mass by 6. Physically, this has the effect that when a certain frequency persists for a long time, then the magnitude of the Fourier transform at that frequency is scaled up more and more. For example, what we're looking at right here is how when you have a pure frequency of 2 beats per second and you wind it around the graph at 2 cycles per second, the center of mass stays in the same spot, right? It's just tracing out the same shape. But the longer that signal persists, the larger the value of the Fourier transform at that frequency. For other frequencies though, even if you just increase it by a bit, this is canceled out by the fact that for longer time intervals, you're giving the wound up graph more of a chance to balance itself around the circle. That is a lot of different moving parts, so let's step back and summarize what we have so far. The Fourier transform of an intensity versus time function, like g of t, is a new function, which doesn't have time as an input, but instead takes in a frequency, what I've been calling the winding frequency. In terms of notation, by the way, the common convention is to call this new function g hat with a little circumflex on top of it. Now the output of this function is a complex number, some point in the 2D plane that corresponds to the strength of a given frequency in the original signal. The plot that I've been graphing for the Fourier transform is just the real component of that output, the x-coordinate. But you could also graph the imaginary component separately if you wanted a fuller description. And all of this is encapsulated inside that formula that we built up. And out of context, you can imagine how seeing this formula would seem sort of daunting. But if you understand how exponentials correspond to rotation, how multiplying that by the function g of t means drawing a wound up version of the graph, and how an integral of a complex valued function can be interpreted in terms of a center of mass idea, you can see how this whole thing carries with it a very rich intuitive meaning. And by the way, one quick small note before we can call this wrapped up. Even though in practice, with things like sound editing, you'll be integrating over a finite time interval, the theory of Fourier transforms is often phrased where the bounds of this integral are negative infinity and infinity. Concretely, what that means is that you consider this expression for all possible finite time intervals, and you just ask, what is its limit as that time interval grows to infinity? And man oh man, there is so much more to say. So much! I don't want to call it done here. This transform extends to corners of math well beyond the idea of extracting frequencies from signal. So the next video I put out is going to go through a couple of these, and that's really where things start getting interesting. So stay subscribed for when that comes out. Or an alternate option is to just binge on a couple 3 Blue 1 Brown videos so that the YouTube recommender is more inclined to show you new things that come out. Really, the choice is yours. And to close things off, I have something pretty fun, a mathematical puzzler from this video sponsor, Jane Street, who's looking to recruit more technical talent. So let's say that you have a closed, bounded, convex set, C, sitting in 3D space, and then let B be the boundary of that space, the surface of your complex blob. Now imagine taking every possible pair of points on that surface and adding them up, doing a vector sum. Let's name this set of all possible sums D. Your task is to prove that D is also a convex set. So Jane Street is a quantitative trading firm, and if you're the kind of person who enjoys math and solving puzzles like this, the team there really values intellectual curiosity, so they might be interested in hiring you. And they're looking both for full-time employees and interns. For my part, I can say the couple of people I've interacted with there just seem to love math and sharing math, and when they're hiring, they look less at a background in finance than they do at how you think, how you learn, and how you solve problems, hence the sponsorship of a 3 Blue 1 Brown video. If you want the answer to that puzzler, or to learn more about what they do, or to apply for open positions, go to janestreet.com/3b1b. For this video, I'm doing something a little different. I got the chance to sit down with Steven Strogatz and record a conversation. For those of you who don't know, Steve is a mathematician at Cornell. He's the author of several popular math books and a frequent contributor to, among other things, Radiolab and the New York Times. To put it shortly, he's one of the great mass communicators of math in our time. In our conversation, we talked about a lot of things, but it was all centering around this one very famous problem in the history of math, the brachistochrone. And for the first 2/3 or so of the video, I'm just going to play some of that conversation. We lay out the problem, talk about some of its history, and go through the solution by Johann Bernoulli from the 17th century. After that, I'm going to show this proof that Steve showed me. It's by a modern mathematician, Mark Levy, and it gives a certain geometric insight to Johann Bernoulli's original solution. Then at the very end, I have a little challenge for you. We should probably start off by just defining the problem itself.
Okay. All right. You want me to take a crack at that?
Yeah, go for it.
Okay. Yeah. So it's this complicated word, first of all, brachistochrone, that comes from two, I have to check. Are those Latin or Greek words? I think.
I'm pretty sure they're Greek.
Okay. So Greek words for the shortest time. And it refers to a question that was posed by one of the Bernoulli brothers, by Johann Bernoulli. If you imagine like a chute and there's a particle moving down a chute being pulled by gravity, what's the path of the chute that connects 2 points so that it goes from point A to point B in the shortest amount of time?
I think what I like most about this problem is that it's relatively easy to describe qualitatively what you're going for. You know, you want the path to be short, something like a straight line, but you want the object to get going fast, which requires starting steeply, and that adds length to your line. But making this quantitative and actually finding the balance with a specific curve, it's not at all obvious and makes for a really interesting problem.
It is. It's a really interesting thing. I mean, most people, when they first hear it, assume that the shortest path will give the shortest time, that the straight line is the best. But as you say, it can help to build up some steam by rolling straight down at first. Or not necessarily rolling. I mean, you could picture it sliding. That doesn't really matter how we phrase it. But so Galileo had thought about this himself much earlier than Johann Bernoulli in 1638. And Galileo thought that an arc of a circle would be the best thing. So he had the idea that a bit of curvature might help.
And it turns out that the arc of the circle is not the right answer. It's good, but there are better solutions. And the history of real solutions starts with Johann Bernoulli posing this as a challenge.
So that's then in June of 1696. And he posed it as a challenge. In particular, he was very concerned to show off that he was smarter than his brother. you know. So he had a brother, Jacob, and the two of them were quite bitter rivals, actually, both tremendous mathematicians. But Johann Bernoulli fancied himself the greatest mathematician of his era, not just better than his brother, but I think he thought that he might be better than Leibniz, who was alive at the time, and Isaac Newton, who was by then sort of an old man, more or less retired from doing math. Newton was the warden of the mint, be something like Secretary of the Treasury nowadays.
And Newton shows him up, right? He stays up all night and solves it, even though it took Johann Bernoulli 2 weeks to solve.
That's the great story, that Newton was shown the problem, wasn't really pleased to be challenged, especially by somebody that he considered beneath him. He considered pretty much everybody beneath him. But yeah, Newton stayed up all night, solved it, and then sent it in anonymously to the Philosophical Transactions, the journal at the time. And it was published anonymously. And so Newton complained in a letter to a friend of his. He said, "I do not love to be dunned and teased by foreigners about mathematical things." So he didn't enjoy this challenge, but he did solve it. The famous legend is that Johann Bernoulli, on seeing this anonymous solution, said, "I recognize the lion by his claw." I don't know if that's true, but it's a great story. Everyone loves to tell that story.
And I suspect part of the reason that Johann was so eager to challenge other mathematicians like Newton is he secretly knew that his own solution was unusually clever. Maybe we should start going into what he does.
Mm-hmm. Yes, he imagines that to solve the problem, you let light take care of it for you, because Fermat in the early 1600s had shown that you could state the way that light travels, whether bouncing off of a mirror or refracting from air into water where it bends or going through a lens. All the motion of light could be understood by saying that light takes whatever path gets it from point A to point B in the shortest time.
Which is a really awesome perspective when you think about it, because usually you think very locally in terms of what happens to a particle at each specific point. This steps back and looks at all possible paths and says nature chooses the best one.
Yes, it is. It's a beautiful and as you say, really an awe-inspiring mental shift. For some people, literally awe-inspiring in the sense that it had religious overtones, that somehow nature is imbued with this property of doing the most efficient thing.
Oh, interesting.
But leaving that aside, you could just say it's an empirical fact that that is how light behaves. And so Johann Bernoulli's idea was to then use Fermat's principle of least time and say, let's pretend that instead of a particle sliding down a chute, it's light traveling through media of different index of refraction, meaning that the light would go at different speeds as it successively went sort of down the chute.
And I think before we dive into that case, we should look at something simpler. At this point in the conversation, we talked for a while about Snell's law, This is a result in physics that describes how light bends when it goes from one material into another where its speed changes. I made a separate video out of this, talking about how you can prove it using Fermat's principle, together with a very neat argument using imaginary constant tension springs. But for now, all you need to know is the statement of Snell's law itself. When a beam of light passes from one medium into another, and you consider the angle that it makes with a line perpendicular to the boundary between those two materials, the sine of that angle, divided by the speed of light, stays constant as you move from one medium to the next. So what Johann Bernoulli does is find a neat way to take advantage of that fact, this sine of theta over v stays constant fact, for the brachistochrone problem.
When he thinks about what's happening with the particle sliding down the chute, he notices that by conservation of energy, the velocity that the particle has will be proportional to the square root of the distance from the top.
And just to spell that out a little bit more, the loss in potential energy is its mass times the gravitational constant times y, that distance from the top. And when you set that equal to the kinetic energy, 1/2 times mv squared, and you rearrange, the velocity v will indeed end up being proportional to the square root of y.
Yes. So that then gives him the idea about, let's imagine glass of layers. And the first one is v1 and the next one is v2. And the next one is v3, and these are all going to be proportional to the square root of y1 or y2 or y3.
And in principle, you should be thinking about a limiting process where you have infinitely many, infinitely thin layers, and this is kind of a continuous change for the speed of light.
And so then his question is, if light is always instantaneously obeying Snell's law as it goes from one medium to the next, so that v over sine theta is always a constant as I move from one layer to the next, what is that path where, such that these tangent lines are always instantaneously obeying Snell's law?
And for the record, we should probably just state exactly what that property is.
Okay.
So the conclusion that Johann made was that if you look at whatever the time minimizing curve is, and you take any point on that curve, the sine of the angle between the tangent line at that point and the vertical, divided by the square root of the vertical distance between that point and the start of the curve, that's going to be some constant independent of the point that you chose. And when Johann Bernoulli first saw this, correct me if I'm wrong, he just recognized it as the differential equation for a cycloid, the shape traced by the point on the rim of a rolling wheel. But it's not obvious, certainly not obvious to me, why this sine of theta over square root y property has anything to do with rolling wheels.
It's not at all obvious, but this is, again, the genius of Mark Levy to the rescue.
Do you want to say a few words about it?
Yeah, well, Mark Levy is a very clever, as well as a very nice guy who's a friend of mine and a terrific mathematician at Penn State who has written a book called The Mathematical Mechanic, in which he uses principles of mechanics and more generally physics to solve all kinds of math problems. That is, rather than math in the service of science, it's science in the service of math. And as an example of the kinds of clever things that he does, he recently published a little note, very short, showing that if you look at the geometry of a cycloid, just drawing the correct lines in the right places, that this principle of velocity over sine theta being constant is built in to the motion of the cycloid itself.
So in that conversation, we never actually talked about the details of the proof itself. It's kind of a hard thing to do without visuals. But I think a lot of you out there enjoy seeing the math and not just talking about the math. It's also a really elegant little piece of geometry, so I'm going to go through it here. Imagine a wheel rolling on the ceiling, and picture a point P on the rim of that wheel. Mark Levy's first insight was that the point where the wheel touches the ceiling, that I'll call C, acts as this instantaneous center of rotation for the trajectory of P. It's as if, for that moment, P is on the end of a pendulum whose base is at C. Since the tangent line of any circle is always perpendicular to the radius, the tangent line of the cycloid path of P is perpendicular to the line PC. This gives us a right angle inside of the circle, and any right triangle inscribed in a circle must have the diameter as its hypotenuse. So from that, you can conclude that the tangent line always intersects the bottom of the circle. Now, let theta be the angle between this tangent line and the vertical. We get a pair of similar triangles, which I'll just show on the screen. You can see that the length of PC is the diameter times sine of theta. Using the second similar triangle, this length times sine of theta again gives the distance between P and the ceiling, the distance that we were calling y earlier. Rearranging this, we see that sine of theta divided by the square root of y is equal to 1 divided by the square root of the diameter. Since the diameter of a circle, of course, stays constant throughout the rotation, this implies that the sine of theta divided by square root of y is constant on a cycloid, and that's exactly the Snell's law property that we're looking for. So, when you combine Johann Bernoulli's insight with this little geometry proof, that's the cleverest solution of the brachistochrone that I've ever seen. And I could call it done here, but given that the whole history of this problem started with a challenge that Johann Bernoulli posed, I want to finish things off with a little challenge of my own. When I was playing around with the equations of a cycloid, something interesting popped out. Consider an object sliding down the cycloid due to gravity, and think about where it is along the curve as a function of time. Now think about how the curve is defined, as this trajectory of the point on a rim of a rotating wheel. How might you tweak the rate at which the wheel rotates so that when the object starts sliding, the marked point on the rim of the wheel always stays fixed to that sliding object? Do you start rotating it slowly and increase its speed? If so, according to what function? It turns out, the wheel will rotate at a constant rate, which is surprising. This means that gravity pulls you along a cycloid in precisely the same way that a constantly rotating wheel would. The warm-up part of this challenge is just confirm this for yourself. It's kind of fun to see how it falls out of the equations. But this got me thinking. If we look back at our original brachistochrone problem, asking about the path of fastest descent between two given points, maybe there's a slick way to reframe our thinking. How would it look if instead of describing the trajectory of a sliding object in terms of its x and y coordinates, we described it in terms of the angle that the velocity vector makes as a function of time? I mean, you can imagine defining a curve by having an object start sliding, then turning a knob to determine the angle at which it's sliding at each point in time, always being pulled by gravity. If you describe the angle of the knob as a function of time, you are in fact uniquely describing a curve. You're basically using a differential equation, since what's given is the slope as the function of some other parameter, in this case, time. So what's interesting here is that when you look at the solution of the brachistochrone problem, not in the xy plane, but in the t theta plane, where t is time, theta is the angle of the path, all of the brachistochrone solutions are straight lines. That is to say, theta increases at a constant rate with respect to t. When the solution of a curve minimization problem is a straight line, it's highly suggestive that there's some way to view it as a shortest path problem. Here, it's not so straightforward, since the boundary conditions that your object start at a point A and end at a point B in the xy space doesn't just look like going from one point to another in the theta t space. Nevertheless, my challenge to you is this. Can you find another solution to the brachistochrone problem by explaining why it must be the case that a time-minimizing trajectory, when represented in t theta space, looks like a straight line?
いてください。花の歌。その日々は夢のように臆病な微笑みと優しい爪を残していた退屈な花びらのように苦しみを忘れて背中でそっと泣いて笑った帰らぬ日々を思うような奇妙な愛しさに満ちた箱庭の中で息を潜め季節がゆくことを忘れ静かな水底のような時間にいた冷たい花びら夜に散り咲くまるで白い雪のようだね切なくあなたの上に降った悲しみをすべて洗いのけてあげたいだけあなたのこと傷つけるものすべて私はきっと許すことはできない優しい日涙が出るほど帰りたいあなたと二人で見上げた花びらが散った月が雲に隠れてあなたは道をなくして泣き出しそうな目をしてたギザギザな心だって二つ合わせてみれば優しいものがきっと生まれてくるわ私を傷つけるものをあなたは許さないでくれたそれだけでいいの the crowd will sing. Now the all king said, long live the king. One minute ahead, the king. Next to walls and close to me, and I discovered that my castle stand up on pillars of salt and pillars of sand. I hear jealous bells are ringing, Roman cavalry cars are singing. Be my mirror. Children of the land, do you hear echoes of truths that once rang clear? Two souls intertwined, one true love they did find, bringing land and heavens near. But flames that burned full bright soon fell dark. Memories dimmed by shadowed hearts. In the waxing gloom did wane the lover's moon, watching as their worlds drift apart. One soul's cry, a passion welling within. Sacrifice, a bind of plea to her kin. Yet this bond of hope by treachery was broke, scattering her words to the wind. Swelling over long seas of blood are a song, and death an afterthought to those who fight for naught. Alone, lying empty, Children of the land and service, why must you turn to empty bliss? Tell me why break trust, why turn the past to dust, seeking solace in the abyss. Tell me why create a circle none can break. Why must you let go the life you were bestowed? This I must you turn to empty bliss? Tell me why break trust? Why turn the past to dust? Seeking solace in the abyss. Tell me why create a circle none can break? Why must you let go the life you were bestowed? This I fear I